The wind is so loud it feels like it has teeth. It's 1995, the North Sea, and we're standing on the Dropner platform, steel grating under our boots, vibrating with every hit of water. The sea is already violent, already. As bad as it gets. And then something happens that doesn't belong in the story we think the ocean is allowed to tell. The horizon compresses. A single face of water rises, too steep, too tall, like the sea is standing up. A wave that shouldn't exist does. And that's the question I want to hand you right now, as if we're gripping the same rail and watching the same wall of water assemble itself out of darkness. When nature looks like it's cheating, is it breaking the rules, or showing us rules we didn't know we were using? Because rogue waves, the so-called freak waves, aren't just a maritime ghost story. They're a stress test of how we model reality. Not just what we measure, but what we assume. And why some events can be physically real, yet statistically invisible, until they're not. So tonight you and I are running an audit. Not of sailors' tales. Of our own confidence. Of the quiet line between rare and impossible. The deck is slick. The air tastes like metal and salt. Somewhere below us, instruments are doing something humans can't, recording the ocean with indifferent honesty. Because the ocean doesn't care what we believe. It only cares what the equations allow. Now, before we chase the monster, we have to understand the ordinary sea. And here's the first trap. The ocean looks like a single thing, but it's not. It's a crowded conversation. Thousands of wave components overlap, different directions, different periods, different phases, each one a little oscillation carrying energy across the surface. Imagine a stadium at night. Every spectator has a flashlight. Each person waves it with their own rhythm and timing. From above, you don't see individuals, you see a shimmering field of light. The sea is like that, many small, lawful motions superposed, stacked on top of each other. And because there are so many contributors, so many little flashlights, something almost magical happens in the statistics. When you add lots of independent random contributions together, you often get a bell curve. In oceanography, under many conditions, the surface elevation behaves roughly like a Gaussian random process. That phrase sounds cold, so let me translate it into a picture you can feel. A Gaussian process is like a drunkard's walk, but with waves. The sea's surface is continuously stepping up and down around an average level. Most of the time it hovers near the middle. Big deviations happen, but they become rapidly less likely the further out you go. If you trust that model, you can calculate how often you should see a wave of a given height. And here's the soothing promise it offers: big waves are rare. Truly enormous ones? Astronomically rare. So rare that on a platform like Dropner, you might expect not to see one in your lifetime. But you and I are on this platform in 1995, and the ocean just produced one anyway. So what do we do with that? We need a baseline language, something engineers and sailors can both point to. Offshore engineering often defines a rogue wave as a wave whose height is greater than about 2 times the significant wave height, HS. Now HS sounds technical, but it's actually deeply human. Significant wave height is the sea state your body remembers. It's roughly the average height of the highest third of waves in a period. Not the tiny ripples, not the boring middling ones, the waves that make you brace, that make you time your steps, that make you feel small. So HS is the ocean's mood, quantified. And a rogue wave, by this definition, is a moment when the ocean delivers something like double that mood. Not a little bigger. Not kinda worse. A different category. If you've ever watched waves from ashore, you've felt the logic of the average. Sets come in. Some are bigger. Some are smaller. The mind builds a prediction. Okay, that's what today's waves are like. A rogue wave is the betrayal of that prediction. And here's the thing, forecasting is not stupid. It's not blind. It's actually astonishingly good at what it's built to do. Modern wave forecasting systems take wind fields, couple them to spectral wave models that track how wave energy is distributed across frequencies and directions, and then they assimilate data from buoys, satellites, and ships. They output evolving sea state, significant wave height, peak period, mean direction. They can tell you, with real skill, that tomorrow will be a 6-meter sea with a long period swell and a crosswind chop. But they don't typically tell you, at 3:17 a.m., at this exact coordinate, a single crest will rise like a cliff. And that's not because we're lazy. It's because the monster wave isn't just about energy. It's about arrangement. It's about phase, the timing of all those components. And phase is like the precise choreography of thousands of dancers. If you know the total energy in the room, you still don't know whether they'll all jump at once. So now we're at the edge of the comfortable model. We've got the bell curve in one hand, and a wall of water in the other. The paradox forms itself. If the sea is random, why do rogues seem to cluster in certain places, under certain conditions? Are they merely the fartail of the same distribution, rare but expected, like eventually, after enough coin flips, you will see a long streak? Or does the ocean have focusing mechanisms, ways to concentrate energy, so that rare becomes not that rare, and impossible becomes we should have known? Let's turn the ocean into a detective scene. The wave that hit Dropner is our crime. The instruments are our witnesses. Our job is to figure out how the ocean built it. There are 3 major pathways, 3 different kinds of focusing, that can make a seemingly ordinary sea assemble an extraordinary wall. And what I want you to feel is that each pathway is lawful. Each one is physics doing exactly what it always does, just arranged in a way our intuition doesn't sample often. First, linear focusing, sometimes called phase convergence. This is the simplest, and in some ways, the most unsettling, because it doesn't require exotic effects. It's what happens when many ordinary waves line up in phase for a moment. Picture pushing a child on a swing. One push from one person gives a certain height. But if 10 people push at exactly the right moments, the swing can surge. The swing isn't breaking rules. It's being driven coherently. In the ocean, each wave component is one of those pushes. Most of the time, their crests and troughs don't align. They interfere, sometimes constructively, sometimes destructively, making the surface a restless mess. But once in a while, by chance, a whole cluster arrives in sync. Crests stack on crests. Troughs deepen beneath them. And for a few seconds, the sea surface stops looking like noise and starts looking like intention. Now, if it were pure chance alone, you might still argue the bell curve will handle it. But the ocean isn't always a single sea. Sometimes it's crossing seas, waves coming from different directions, generated by different storms, overlapping. That broadens the spectrum, the range of components available to align. And with more components, you increase the number of possible alignments. The ocean becomes a bigger orchestra. And bigger orchestras have more ways to accidentally hit a thunderous chord. Here's the next question you should be asking, because it's the one engineers quietly ask at 2 a.m. While staring at design curves, if phase alignment can do it, how long does the alignment last? Seconds. Sometimes less. But seconds is all a ship needs. Seconds is all a platform needs to feel a load it wasn't designed to feel. Second pathway. Focusing by currents and bathymetry. This one is deeply physical in a way you can almost hold in your hands. If the first pathway is about timing, this one is about terrain, the invisible geography under the water and the moving rivers on top of it. Start with a simple human analogy. Walk up an escalator that's going down. Your steps get shorter and more frantic. You're still walking, but the environment is stealing your progress. Waves do something similar when they travel against a current. An opposing current shortens the wavelength and steepens the wave face. The wave energy is still there, but it's squeezed into a smaller horizontal distance. The wave stands up. This is why sailors have a phrase that feels like folk wisdom, but is actually fluid dynamics. Wind against tide makes it nasty. It's not just nasty, it's focusing. Scale that up to ocean highways like the Agulhas Current off South Africa, or intense features of the Gulf Stream. These currents can be fast enough, structured enough, to act like conveyors that compress wave trains. If wind-driven waves meet a strong opposing flow, their group velocity changes, their spacing changes, and their steepness increases. A sea that looked manageable on a forecast map can become a trap. And then there's bathymetry, underwater topography. The seafloor isn't flat. It has shelf breaks, sandbanks, ridges, trenches. When wave energy passes over varying depth, it refracts, bends like light through glass. If you've ever used a magnifying glass to focus sunlight into a bright point, you understand the metaphor. The lens doesn't create energy. It concentrates it. Underwater features can act like lenses for wave energy. They can steer wave rays toward convergence zones, building higher waves where the geometry piles energy up. Combine that with a current, and you're not just rolling dice, you're loading them. So ask yourself, if a region has a known strong current and known bathymetric features, would you expect rogues to be uniformly random there? Or would you expect hotspots? Places where the ocean is more likely to stand up and show teeth? Suddenly, the clustering reports, those stories sailors tell in hushed tones, start to look like data. Like pattern. Third pathway, nonlinear focusing, often discussed through something called modulational instability. This is the one that feels almost alive. It's the ocean taking a wave train and deciding, through the mathematics of nonlinearity, to clump its energy into a few peaks. Let's define nonlinear, without hiding behind the word. A linear system is polite, effects add. Two waves meet, and you can just sum them. A nonlinear system is rude in a fascinating way. The system changes its own rules as it goes. Bigger waves behave differently than small waves. The response isn't proportional. And that's where surprise lives. Here's the intuition, and I want it to feel like something you've experienced in traffic. You're on a highway. Nobody crashes. There's no visible cause. But suddenly brake lights bloom, and a traffic jam forms out of nothing. That jam is a clumping of cars, energy and motion concentrating into a dense region, created by tiny differences in speed and reaction time, amplified by feedback. In wave trains, under certain conditions, tiny modulations in amplitude can grow. A slightly taller crest can travel with slightly different speed characteristics than its neighbors. Energy flows into it. It grows taller. Its neighbors lose energy and shrink. The wave train stops being evenly distributed and becomes lumpy, few big peaks and many small ones. This isn't mysticism. It's mathematics that shows up in many places, in optics, in plasmas, in Bose-Einstein condensates. The same family of equations, like the nonlinear Schrödinger equation, describes how wave envelopes can self-focus. The ocean, the laser, the quantum wave function, different media, similar logic. Energy wants to localize when the conditions invite it. Now, modulational instability isn't always active on the ocean. It requires certain spectral narrowness, steepness, and coherence. Real seas are messy. But in the right patch of water, under the right wind, with the right wave train, you can get nonlinear self-focusing that produces a crest that looks like a mistake. So we have three suspects: phase alignment, current bathymetry focusing, and nonlinear self-focusing. The truth, almost always, is that rogues live at the intersection. The ocean doesn't pick one mechanism and stick to it like a textbook problem. It layers them. It stacks them. It composes them. And now we return to Draupner, because this is where the audit becomes unavoidable. Before the mid-1990s, rogue waves were in an awkward state. Sailors reported them. Ship damage suggested them. But the scientific community, especially the engineering side, tended to treat them as outliers, anecdotes, or mismeasurements. It wasn't that anyone thought sailors were liars. It was that data is brutal. If your models say an event is essentially impossible, you start hunting for alternative explanations: instrument error, survivorship bias, exaggeration. Then Draupner happened. Not just a wave, but a wave captured by high-quality instruments on an offshore platform. A measured time series. A crest elevation that refused to politely fit inside the Gaussian expectation. It was like finally catching lightning in a calibrated bottle. And in that moment, right now, with us on the shaking steel, the field shifts. Because once you have a clean measurement, you can't dismiss it as myth. You have to update your model of the world. Here's where the story becomes more human than technical. Updating a model sounds easy. People say it like it's a software patch. But it's not. It's admitting something about your own mind, that your sense of what's reasonable was trained on the middle of the distribution. On the average day. On the data you actually saw. And the tail, the extreme end, was always there, waiting. So why is forecasting rogue waves still hard, even after we accept they're real? Why can't we just build a rogue wave detector and be done with it? Because the ocean is a high-dimensional chaotic system. And chaotic doesn't mean random. It means sensitive. In chaos, tiny errors in initial conditions grow. Think of it like trying to predict the exact shape of smoke from a candle. You can predict that smoke will rise. You can predict its average behavior. But the exact curl, the specific loop at a specific second, depends on microscopic details. The ocean is that, but scaled up to kilometers, and powered by storms. And here's the technical knife edge. Most operational models output spectra, how much energy exists at each frequency and direction. That's immensely useful, but it discards a crucial ingredient for predicting a single monster crest at a single point, phase information. The exact timing relationships between components. Without phase, you know the ingredients but not the recipe. So even with perfect knowledge of the spectrum, you may not know whether, 5 minutes from now, those components will align into a single coherent shove. And 5 minutes is exactly the scale where lives are decided at sea. Then there's the problem of intersection. Rogues tend to appear when multiple factors overlap. Crossing seas plus strong currents plus nonlinearity plus local wind bursts. Rare combinations, and the ocean is vast, measurement is sparse. Buoys are points. Satellites have revisit times and limitations. Platforms are rare. Ships move. We often have the right equations. What we don't have is the right observation of the state, at the right resolution in space and time, to feed those equations. We're trying to forecast a lightning strike with a weather map. And then the most treacherous part, extreme value statistics. This is where human intuition snaps. We calibrate our expectations on normal data, on the waves we see most often. We build designs and safety margins using distributions fit to limited samples. But safety depends on tails we barely sample. The rarest events are, by definition, the ones you almost never measure. So you end up with a problem that is both scientific and philosophical. How do you prepare for what you have not yet seen, without hallucinating monsters everywhere? This is the tension. If you overreact, you paralyze engineering with impossible requirements. If you underreact, you build a world that fails in the one moment it matters. And that brings us to the cleanest, most important insight, the one that hits like cold air in your lungs when you finally stop arguing with the ocean and start listening. The ocean isn't violating physics. It's exploiting physics, briefly, like a lens focusing sunlight into a burning point. That impossibility is our mental model, not the water. Think about what that means. We humans love rules because rules feel like control. We hear Gaussian, and we relax. We hear 1 in 10,000, and we treat it like never. But nature doesn't respect our emotional interpretations of probability. A rogue wave is not a miracle. It's a lawful alignment of lawful parts. Now step back with me from the deck. Let the roar of the sea fade a little. Here, instead, the quieter implication, rogue waves become a parable about prediction itself. Knowing the rules does not guarantee knowing the next outcome. You can know Newton's laws and still not know exactly where the double pendulum will swing in 30 seconds. You can know the Navier Stokes equations and still not know which eddy will be born on the edge of a current. And you can know the wave equations and still be surprised by a single crest. Random is not the same as structureless. That's the philosophical gift hidden inside the terror. Noise can produce momentary order. Coherence can rise out of chaos, gleam for a few seconds, and vanish before you can name it. Like a face you think you see in a crowd, except this face can crush steel. So what do we do, practically, if we can't point to a map and circle? Rogue wave at 317. We build layered defenses. We stop searching for a single magic detector and start building a system that respects uncertainty. It looks like better directional wave measurements, because direction and crossing matter. It looks like current mapping, because opposing flows and shear can be the difference between rough and vertical. It looks like higher resolution coupled models that let winds, waves, and currents talk to each other rather than living in separate silos. It looks like probabilistic risk forecasts, maps not of certainty, but of elevated danger. It looks like alert thresholds for focusing friendly conditions, crossing seas above some angle, steepness above some limit, strong opposing currents, bathymetric hotspots. And most of all, it looks like intellectual honesty. The humility to say, we do not forecast a single crest, but we can forecast the conditions that make that crest more likely. We can shift from pretending we know the future to honestly estimating risk. Now I want to bring this home, not to the sea, but to you. Because rogue waves are not just an ocean story. They're a universe story. The universe builds extremes the same way the ocean does. Not by breaking laws, but by arranging lawful pieces into rare alignments. A star doesn't cheat when it collapses into a supernova. It follows gravity and nuclear physics into a runaway. A black hole doesn't violate reality. It's what reality does when mass concentrates enough that spacetime can't stay flat. Even life, cells forming organs, brains forming thoughts, looks impossible until you see the lawful feedback loops that focus chemistry into identity. Rogue waves are that lesson, delivered in salt water. They tell us, your model is not the world. Your averages are not your guarantees. And the tails of your distributions are where reality hides its sharpest teeth. So here's the synthesis, what we now know, standing here between fear and understanding. Rogue waves are real. They are measurable. They can emerge from linear phase alignment, from current and bathymetric focusing, and from nonlinear self-focusing, and most dangerously, from combinations of all three. They feel impossible because our intuition lives in the middle of the curve, while the ocean sometimes lives in the tail. Now the contemplative takeaway. I want you to run a small experiment in your mind the next time you hear the word random. Imagine 1,000 tiny causes, tiny waves, moving through your life, conversations, stress, sleep, weather, timing, chance. Most days they average out. You get something like normal. But once in a while they align. You have a day that changes you. A moment that feels like it came from nowhere. A crest. Was it magic? Or was it physics, lawful pieces briefly finding the same phase? And now the next great question, the one that opens the next door. If reality can generate these sudden, focused extremes from ordinary components, what other, impossible, events are sitting quietly inside our models, waiting for the right alignment to step out of the dark? If you want to keep going, I'm putting a related investigation on the end screen. Watch that next, because it deepens this exact idea of prediction versus reality, and it'll change how you see uncertainty. And if you want a reason to subscribe that actually matters, this channel is where we audit the stories our equations tell, and we update them when nature brings new evidence. New episodes are built to make you feel the awe and learn the rigor, both. One question for you, and I want a simple answer in the comments. If you had to bet, which mechanism feels most responsible for rogue waves, phase alignment, currents and seafloor lensing, or nonlinear self-focusing? And why does your intuition pick that one?